Okay, now we go on to estimating a population variance. And here, the distribution that we're using is called chi-squared. When it comes to chi-squared distribution, requirement is straightforward. The population must be normally distributed. Doesn't matter what the size of n is. N can be as large as you want. It's still, you cannot use chi-squared unless it's normally distributed. And if you want to calculate chi-squared, and of course that's the symbol for chi-squared, it equals n minus 1 times s squared divided by sigma squared, where n is, like always, the sample size, s is the population standard, let's start over. S represents the standard deviation of the sample, and sigma is the standard deviation of the whole entire population. It turns out that the confidence interval for the population variance, sigma squared, is n minus 1 times s squared over chi squared sub r, we'll talk about that, is less than sigma squared, which is less than n minus 1 times s squared over chi squared L. And if you just want the confidence interval for the population standard deviation sigma, well, you just take the square roots of all three sides. The square root of the middle, that is the square root of chi squared, is just sigma, excuse me. The square root of sigma squared is just sigma. Okay, so the big difference here is we're not estimating the mean. We're not estimating the mean. We are estimating the standard deviation. We're not estimating the mean for the true population, but rather their standard deviation. That's the big difference here. And you should know this formula in the middle. Actually, you should know the one in the bottom. The confidence interval is that. Okay. And of course, we'll have to talk about how you find these chi-square values. You have a chi, just like you have a table for normally distributed samples and t-distribution. You have a table for chi-squared. Now, suppose you have this. Suppose that the salary of 41 college grads, has a sample salary of $67,200 with a sample standard deviation of $18,277. The problem is to estimate the standard deviation. Estimate the population standard deviation. Okay, let's write that down. Estimate the standard deviation of the entire population. That is sigma. So when it comes to that formula, the square root of n minus 1 times s divided by chi-squared sub r is less than the standard deviation, sigma, which is less than the square root of n minus 1 times s over chi-squared sub l. Well, we know n, and we can easily take away 1, and we're given s. In this case, x is 18,277. The right side, we know n. We can easily take away 1 from that. We know s. What we don't know is the chi-squares. And the slight typo, the salary of 41 college graduates. So we randomly selected 41 college grads, and we computed their mean, average salary, and the standard deviation associated for these 41 college grads. So what we want to know is, what is chi-squared L? What is chi-squared L? And what is chi-squared sub r? Well, again, we have the degree of freedoms is n minus 1. It's 41 minus 1, which is 40. So you go to the chi-square table, and you go to 40. But of course, I did leave out one thing. Just give me one moment. We want to be trying to figure out the best way around this. We want 95%. Okay. We want 95% confident interval. Using a 95% confident interval. Okay. So what that tells me is, in the middle, we have our 95%. There's 5% left over. 0.05, 0.05. Now, actually, probably the best way to look at this is that you have, let's deal with just the right side. Up to here, you have 97.5. And to the right, you have 0.05. Or, I have a typo there, you have 0.975 of the area. So when it comes to the left one, for chi-squared L, you look under 0.975, and you go to the degree of freedom, which is 40. Under 0.975, you go to 40, and you get 24.433. And to the right of that cutoff, you have 0.05. So you looking under 0.05 under the chi-square distribution table. You go down to 40, and you get 55.758. 55.758. So they want 95% confident interval. Let's go over this again. how you decide which headings to use under the chi-square table. Day 1, 95%. So in the middle, you have 95%. So from the far left all the way to the 95%, well, you remember, if 95% is in the middle, you have 5% left over. 2.5% goes here, 2.5% go here. So all the way up to here is 97.5%, 0.975. And to the right of this line is 0.025. 2.5% equals 0.025. 2.5% happens to equal 0.025. And that's what you use. For the left, you go to, for chi-squared sub L, you look under 0.975 and you go down to 40. N minus 1 is 40. And you get your number. And then you look under 0.025, go down to 40, and you get your number. Okay. And now it's just plugging in. Now we just plug in. Okay, let me just move this number over a little bit. Chi-squared R is 55.758. Okay. So now we use the formula at the very bottom. N minus 1 is 40. N minus 1 times S. S is given to be 18,277. And this gets divided by chi-squared R, which is 55.758. You take the square root of that mess. And that's going to be less than sigma, which is less than, and we do the right-hand side. Square root, the top's the same. N minus 1 times sigma is still 40 times 18,277. And we divide by chi-squared sub L, which is 24.433. Okay, let me erase this bottom. And if you do this arithmetic, the left-hand number will be 15,005. The right-hand number is 23,385. And sigma, their standard deviation for the true population, will be somewhere in between there. So the big difference in this section, and it is a big difference, is we are not finding or estimating the mean of the population. Now we're estimating the standard deviation for the population. And we have that nice simple formula to use. Okay, do a couple more problems. Okay, let's get into these quarters and their machines, the video machines. So quarters are currently minted with weights having a mean of 5.60, 5.67 grams. So that's mu. Mu is 5.670 grams. This is currently. And the standard deviation is 0.062 grams. But new equipment, so let me not call this current, call that the old, before. Before and now. The before picture and the now picture. Now, new machine is being tested in an attempt to improve quality by reducing the variation in the weights. A random sample of 24 quarters from the new equipment is tested, and the sample, so that's X bar, the sample, well actually we don't need X bar, and the sample, from the sample, it turns out that the standard deviation is 0.049 grams. We want to use a 95% confident interval, a sigma. There are standard deviation weights of quarters made with the new equipment. Okay. So we want to find a 95% confident interval, or sigma. So now we know that n is 24, and we know that sigma is 0.049. Basically, we need to find chi-squared L and chi-squared sub R. And in fact, due to the space that I'm going to need on the bottom, I'm going to put these numbers up here. Now, since we want a 95% confident interval, the best way is to draw this picture. We have 95% in the middle. Remember, the criteria to use this technique, the requirement is it must be normally distributed. So if it's 95% in the middle, that leaves 5% left over. So 2.5% goes to the left, and 2.5 goes in the right tail. So in just the right tail, to the right of the cutoff here, is 2.5%, or 0.025. And all from the far left up to that cutoff, this being the cutoff, is 97.5%. 2.5% plus 95%. 97.5%, which is 0.975. And the degree of freedom is n minus 1. It's 23. So for chi-squared L, we look under 23 and 0.975 on the chi-squared distribution. The top area is 0.975, and I go down to 23, and I get 11.689. 11.689. And chi-squared R, I go to just 0.025. And I go down to 23, which, if I'm reading this correctly, is 38.076. 38.076. Okay, let's get rid of our side work. Now we're ready to do this. All I needed was sigma, n, and the two chi-squares. So now I just plug in. I want to check something, please. Okay. So basically, I know that sigma is in between n minus 1 times s divided by chi squared sub r, square root of that, and in n minus 1s over chi squared L. Sigma is in between that. Well, n is 24, so n minus 1 is 23 times s, which is 0.049, divided by chi squared r, 38.076, square root of this, less than sigma, which is less than. Well, the top doesn't change. It's still n minus 1 times sigma, divided by 11.689. Well, turns out that the left number is 0.03962. And the right number, if I didn't make any silly mistakes, is 0.0687. And here is your confidence interval for sigma. Let's try one more. Turns out that, or it seems like it turns out, that whenever it snows, of course, people have to go out and remove the snow. And you know, if you don't exercise very much and then you have to go out and move a couple of tons of snow, it may be too much for you and maybe you have a heart attack. In case you have a heart attack, if your heart rate gets too high. I guess, you know, I'm no doctor, but I guess there's other ways to have a heart attack, but one way to have a heart attack is for your heart rate to just go too high. I mean, think about the engine in your car. If you rev the engine too high for a long period of time, it's going to blow the engine. Okay, your heart's a pump. If you overwork the pump, it's going to cease working at some point. So there were two studies done. One where they sampled the maximum heart rate of people who manually moved the snow, manual snow removing, and they did a study from a sample of people who used electric snow thrower. So one person manually removed the snow, the other person had electronic equipment moving, well, had mechanical equipment moving the snow. And we had the maximum heart rate. Heart rate. The maximum heart rate. And the sample sizes were both the same. They used a sample of 10 people. In the first case, the average heart rate was 175, and the standard deviation was 15. And in the second case, where they used an electric snow thrower, the average heart rate was only 124, and the standard deviation was 18. And they wanted to know, basically, what were the true standard deviations between them. In each case, what was the standard deviation between using some confidence? Okay. So again, to do this, you have to know the chi-squares. Well, chi-squared r well, let me just work backwards for a moment, please. Okay. For both cases, use 95% confident. For both cases, use 95% confident. Okay. So chi-squared r. And actually, let's do the left one first. And chi-squared L and chi-squared R. What are they? Since we're using 95%, that means in the right tail here, in here, is going to be 0.025. Well, there's 0.975 left over for everything else. So under 0.975, that's left, under 0.975, we go to n minus 1. N is 10, so we go down to 9. 0.975, we go down to 9, and we get 2.7. 2.7. And if you go all the way, if you look under 0.025, go down to 9, get 19.023. 19.023. And while we're at it, so chi-squared L and chi-squared R will not change in the bottom, because it's still 95% and the sample size is still 10, so the degree of freedom is still 9. That's not changing for either problem, for either half of the problem. So on the left side, we know that the formula is n minus 1 times s, n minus 1 times s over chi-squared L, which is 9 times 15 over, excuse me, this is R, over 19.023, and that number happens to be 10.317. That's less than sigma, and sigma is less than n minus 1 times s divided by chi-squared left, which is 2.7. And if you do that division, you get 27.38. 27.38. So sigma is in between 10.317 and 27.318. Now, let's go down to the electric snow thrower statistics. N, since n is 10, n minus 1 is 9, times the standard deviation, which is 18, divided by chi-squared r, which is still 19.023, it turns out that that number is 12.38. And that's less than sigma, which is less than n minus 1 times sigma divided by chi-squared left, or L, which is 2.7. And when you do that division, you don't get less than, excuse me, but you get equal to 32.86. So the standard deviation is in between 12.38 and 32.86. And, you know, looking at the intervals, 10.317 to 27.38, and 12.38 and 32.86, they seem very similar. I don't really see much of a significant difference between the two. Okay, this finishes the section for chi-square distribution. That's where you want to estimate the population standard deviation or the variance. So, which means, excuse me, I should be taking the square root of this. I'm sorry. I should be taking the square root of these values. I did mess that up. And if we go back, I did put the square root symbols. Okay, that finishes this section. Good luck with it.